So this is on how to interface your custom robot using ROS. So this disclaimer, this will be like a how you can interface like from the scratch, or like this will be like an entry level, let's say like a tutorial or something like that. So the idea is everyone here who is listening should be able to do that very easily with the hardware, even with limited hardware resources. And if you have a custom robot, you should be able to interface it using ROS and use all the capabilities all other speakers introduced before. So before moving on to the slides, just a quick recap on this image before. So this is our leg-wheel hybrid robot during a testing stage. So you can see the wiring is quite messy, but here you can see 3 Arduinos. So one Arduino Nano for each servo motor, and there's another Arduino here that is basically a ROS node that we use to do the testing of this leg. So yeah, basically like Arduino and Arduino Uno in a ROS node. So let's start. So what do I mean by a custom robot? So a custom robot can be something very simple, maybe like a servo motor fixed into Arduino, or maybe it can be a quite complex project like this hexapod robot from CSIRO with so many vision tasks and so many servo motors and likewise. But actually the term complex, it's quite tricky. Even this Arduino-based setup, servo motor setup, even though it is simple in hardware, it can be quite complex in control systems domain. So maybe there are lots of cool control systems running on this one. Let's assume this one as a basic one. Basically, to control a servo motor, you are controlling the position of the output shaft, and basically you are giving a pulse width modulated signal through the Arduino, right? So like a custom robot can be even simple, something like that, or something very complex. And before starting with ROS and everything, so we have to decide on our hardware, right? So if we know what kind of a system we are developing, for example, if you are developing a robot like this, you have vision systems and so on, you need lots of computational power. So this robot actually is running on this x86 Intel NUC, or it is basically like a mini PC, because to do all the computations of vision, all this trajectory planning, you need lots of computation power, like 16 gigabytes of RAM and lots of power as well. But if you are like using a very simple project, maybe like a servo motor control or something, you can end up with something like Arduino Uno that has like only like 2 kilobytes of RAM and not much of peripherals, and very power efficient. So in middle, if you are developing something middle, you can decide which kind of hardware is good for you. Maybe like a Raspberry Pi. If you want a simple camera, maybe a Raspberry Pi 3 or 4 will be a good starting point with decent RAM and other peripheral capacity. So yeah, you will be deciding the computational power. So the takeaway message is: does the hardware matter if you're going to interface it with your robot? The short answer is no. Given, let's assume you have a computer that is capable of running ROS, then this robot's hardware is not going to actually matter. So in robotics, like the pipeline, the term pipeline of developing something is quite powerful, and we want to focus on that. And let's start from the basics. Servo motor control using Arduino. So basically you have an Arduino, and let's say you have a variable resistor. You want to rotate it, and according to that, the motor should turn to some angle. So you have the hardware setup. And basically what you do is you plug your Arduino into the personal computer you're using, and through serial communication, you can like power it up, and you can visualize everything like from command in lines. And you can have a decent setup or pipeline like that. So the Arduino code you will be uploading here will be something like you are going to do some analog read, and you are going to map that analog read value to a angle of this servo motor, and you are going to command it through my servo library, right? So most of you will be familiar with this one. So let's make it a little more advanced. So rather than one servo motor, you have now 1, 2, 3, 4 servo motors. Still, you can use an Arduino because you can plug all of them to the analog, the PWM outputs of the Arduino board. One limitation here, if you are using an Arduino, the latency will be a bit high. But yeah, you can use a setup like this still. So if you have a advanced setup like that, still the pipeline is same. So you can use the laptop and Arduino software to communicate and to control the this robot arm that you are developing. So one thing is, if you want to set, if you have a very nice robot like this, do you want it to be just limited to Arduino? So you have seen lots of trajectory planning and videos like that, and it would be really great if there are options like that to control your advanced robot like that. So for example, like if you control this motor here, it is going to change the position of all these motors, or you're going to rotate the entire arm, and if you want to adjust this again, there will be some decent control as well for this robot to work, because you have to basically control 4 motors, right? So yeah, not that great, but you can make it work. So if you can make it work, why ROS? So let's assume for a second, this Arduino is not an Arduino, but a ROS node. So what kind of capabilities you are going to get? So one thing is, no need to upgrade your hardware. So that is a great relief, I guess. So if this is a ROS node, you can issue commands as ROS topics. So you are not limited to Arduino software now. You can issue commands as ROS topics. And maybe if you have a SolidWorks design, if you can build a SolidWorks design, you can have real-time visualization. So it would be really cool if you can see your visualization and the real hardware working side by side, right? So that would be really great. And you can see even without making the actual robot move, you can see from these visualizations using ROS. And maybe you can do hardware simulations as well, physics simulations as well. So another thing is, you can teleoperate from keyboard. You can give keyboard inputs. You can use keyboard and mouse to control these motors. And maybe you don't have to stick with just C++. You can either use Python, or if you have other libraries that are going to control your robot, great, you can use them as well if this is a ROS node. And you can also use state-of-the-art open source trajectory planners, so you don't have to do the controlling yourself. So even without knowing inverse kinematics, forward kinematics, you should be able to make nice patterns using what Sakuna mentioned about trajectory planning, right? So that's great. So we assume this is a ROS node. So can we actually make it work? So it sounds advanced, but absolutely it is not. So basic things you have to do is, you have to install something called ROS serial. So basically you have to install some packages in ROS. So this is in Linux version, so or Ubuntu. In Ubuntu, so these commands are related to Ubuntu. And when you are doing that, so you have ROS serial setup, and you have to upload a code to the Arduino so that it knows it is going to be a ROS node. So you can do that by using just the Arduino software itself, just to upload the code. So here you have to include just like if you are including another library, let's say a servo library, or like a motor library, if you have something like that, you have to from third parties, you have to install it to Arduino libraries. Likewise, you have to install this ROS library, and then it is basically a matter of including this header files ros.h. So afterwards, your Arduino will be behaving like a ROS node, and you can give all the commands like subscribe and publish and anything like that through this command. So I hope this is clear, and basically now you can make this Arduino a ROS node. So a summary, if you take a summary, okay, now this is a ROS node, we understood how to do that. And then the ROS master is going to be your computer. So you are going to have it plugged into your computer. And basically what you're going to do is you are going to give ROS topics, what we call as sensor message joint state. Joint state is like something anyone who is using ROS knows. So if you have any trouble with that, you can just search. So most likely if you encounter a problem with joint state, how to publish to joint state or anything like that, there will be a very high chance someone has already debugged it and put in ROS wiki or ROS answers, some kind of page, something like that. And so what you're going to do is you're going to make a custom C++ or Python ROS node that is going to do the controlling part as you want, or you can use something like a trajectory planner, and it is going to publish these joint 1, 2, 3, 4 values in like a standard manner in ROS. Then you can use that values just to either to transmit through that wire to your ROS node or your Arduino Uno. And it is going to map these joint 1, 2, 3 values to PWM signal 1, 2, 3, and 4. And also this joint state topic, you can use it to visualization, so any kind of tasks like that. So that is the power of ROS. So yeah, even if you have an Arduino, you can start with ROS, so that's great. But what if you have more computational power? It's even more great. So one issue with Arduino is you cannot make it a ROS master. So this has enough computational power to become a ROS node, but it cannot have standalone ROS master running because of that issue. So you have to have a computer where the ROS master is running. But if you have like a powerful embedded system like a Raspberry Pi 3, you can install Ubuntu in this Raspberry Pi, and you can install ROS on top of Ubuntu, and then you can initialize a ROS master in this Raspberry Pi 3. So in that scenario, no, you don't need, you won't be needing a separate computer to run this. So that would be great. Yeah. So let's assume that scenario. So you have a Raspberry Pi 3, what you can do. So you must have seen like very nice remote control cars. And if you have a remote control car that has cameras, you can see where you are going. And if you can control it by your computer and you can see where it is going, and maybe it has some autonomous methods like it can detect obstacles and brake, that would be really good. Let's forget about research aspects. Even as a hobby, that would be a really great project, right? So with ROS, you can do that and just have the hardware and your computer separate by using a Wi-Fi router, because ROS handles communication between ROS master and ROS nodes over Wi-Fi communication as well. So you don't have to have like a long wire going from the computer to the remote control in the sense like computer control, let's say. So if you have this kind of a setup, the ROS master is going to be in your computer, and you can have like various ROS nodes, maybe ROS nodes for navigation. You can get from other, maybe from what other people have developed, and you can have visualizations. What is the angle of your front wheels? What is the steering angle? What is the speed I'm giving? And like you can visualize the camera, and yeah. So all this is possible through a Wi-Fi router in the basic sense. And if you have a camera mounted to the Raspberry Pi, and if you have motor controllers and servo controllers, there's a very high likely chance that these manufacturers of these motor controllers and servo controllers have a ROS node developed already, or someone else has developed already. So you don't have to go and wrap ROS and have them develop yourself. Most likely you will come across ROS libraries, or what we call as ROS drivers for these motor controllers. So basically all you have to do is give the motor velocity commands as a topic, and it will be decoded by these ROS drivers very easily. Yeah. So that sums up it. What are the capabilities, and the capabilities beyond this is like all the ROS projects we have shown you in the beginning of this session. Like so many research aspects, you can use advanced versions of this one. So just before wrapping up, so even in our university of Moratuwa, there are some robots called Sumo that we used to have for practicals. So this robot developed by Pololu, it has like a microcontroller by Atmel A32U4 chip. It is basically like Arduino compatible chip, and we have like ROS strapped it using ROS serial packages, as mentioned in this presentation. And basically, we have given ROS capability for these motors, which were earlier Arduino compatible, and using them, we can use them for use them to teach autonomous systems, and so many capabilities are there. So, for example, like when this robot is going, we can have visualizations like this, so we can use for other control tasks. So that kind of sums up how to control the robot, how to control, how to interface your custom robot with ROS. So